So let me start the lecture for today. Let me just briefly talk about what we were talking last time. In the last lecture, we were looking uh, at the diversity order and bit rate of multiple antenna systems. So what we said is the following. We said if I have a multiple antenna system, that is with L receive antennas, sorry, just trying to figure out something with respect to my pen here. I'm not able to write. Yeah. So what we are saying is if you have multiple antenna system, we have seen this system. If you have multiple receive antenna, and this is the system that we had seen where we had a receiver and we had a transmitter, and we said that when you have multiple receive antennas, specifically let's say we have L antennas, that is, let's say we have L antennas, then what we said is that the bit error rate, we said that the bit error rate will decrease as 1 over SNR to the power of 1 over SNR to the power of L. Okay, and this L, that is, we said that this L is known as the diversity order of the system. This L, this is known as the diversity. That is, we said that this results in a significant decrease of the bit error rate as the number of antennas increases. Basically, the bit error rate keeps decreasing. For one antenna, it is 1 over SNR. For two antennas, it is 1 over SNR square, and so on and so forth. For L antennas, it is 1 over SNR to the power of L. And we said this diversity order, or this phenomenon that the bit error rate is decreasing as 1 over SNR to the power of L, this arises because of the probability of deep fade. We said that because of L independent antennas, we have L independent fading paths, we have L independent fading paths. As a result of these L independent fading paths, what we have is that the probability that the probability that wireless communication is in a deep fade is significantly reduced. We have looked at this, we have calculated what is the bit error rate, what is the bit error rate for a fading wireless channel, what is the bit error rate across a fading wireless channel with multiple antennas. Alright, so these are all the different aspects we have looked at. So far we have looked at what is a fading channel, how to model a fading channel, that is the Rayleigh fading channel. We have seen what is the bit error rate performance of a Rayleigh fading channel. Then we have seen what is the bit error rate performance of a fading channel with multiple antennas. Then we have seen what is the probability of deep fade, how is this probability of deep fade varying. and what is the reason for the probability of defect, and also finally we have seen what is the notion of diversity order. So that completes our discussion on diversity. What I'm going to talk about next is I'm going to talk about how to characterize the wireless channel. So what I'm going to start talking about next is basically characterization or what I'm going to talk about is essentially what are the parameters. What are the parameters which characterize the wireless channel? What are some of the parameters which characterize the wireless channel? For instance, in the very first lecture we have seen that the wireless propagation environment is a multipath propagation environment. For instance, let's say I have a base station. And I have a, is there no audio? I think please contact. So I have a base station and I have a base station, and a base station is basically transmitting to a mobile, and we said that there is not only a direct line of sight path, but there are also several non-line of sight paths that are occurring. So let's say there are some buildings, there are some trees. So basically what we have is we have several scatterers. So there is a signal. So there is a direct path which is the line of sight, and these are the non-line of sight paths. These other paths which are here, which are being reflected or scattered, these are the non-line of non-line of sight paths. So we have a direct path or we have a line of sight path, and we have we have several non-line of sight paths. And these non-line of sight paths arise because of the scatterers. For instance, there are these trees and buildings which reflect or scatter the wireless signal. These are known as scatterers. Alright, so there are several scatterers in the path. So this is the base station. This is the mobile station, and what we have is we have several non-line of sight paths which are basically arising because of the scatterers in the path of propagation. So we have several non-line of sight paths which are arising because of the scatterers. So this is also, remember, this is also known as multipath propagation. In the context of wireless communications, remember, this is also known as multipath this is also known as multipath propagation. In the context of wireless communications, this is also known as multipath propagation. Alright, so we have multipath propagation. Now, because of the multipath propagation, what is essentially happening, remember, is that we have multiple signal components arriving at the receiver. So therefore, what we have is remember we looked at the channel impulse response. Does anyone remember the channel impulse response? How we model the channel impulse response when we model the wireless channel? Does anyone remember the wireless channel impulse response? Can someone remind me what is the wireless channel impulse response? Does anyone remember? That is, if I model the wireless channel as an LTI system, what is the channel impulse response of the wireless channel h of t? Does anyone remember? Okay, that is fine. We said that the wireless channel is basically the sum of several impulses, because remember there are several multipath components. That is, there is a signal copy, there is a slightly delayed and attenuated version of the signal copy, another delayed and attenuated version of the signal copy. So there are several copies of the same signal, and we said that each copy corresponds to an impulse. That is, impulse is nothing but signal but delayed and attenuated. So we have several copies that are basically delayed and attenuated. Therefore I can represent the impulse response as a sum of delayed and attenuated impulses, right? So this is t minus tau I equal to 0 to L minus 1. So we said that the impulse response of the wireless channel is basically the sum of several impulses. Each impulse corresponds to the attenuation AI, and each tau I corresponds to the delay. So basically, and therefore now I can also do another thing. I can also basically, if I want to find out what is the power that is associated with each multipath component, that is the power that is associated by each multipath component, I can set Gi, the power associated with multipath component, as magnitude Ai square. If Ai is the amplitude, the power Gi equals magnitude Ai square. So Gi, I am saying, is the gain. It's the gain or power associated with ith multipath component. Gi is the gain or power associated with the ith multipath component. So basically I can write this also as the channel power profile. The channel power profile is this is the channel power profile. What is the channel power profile? The channel power profile basically simply says that there is a power of Gi, that is the multipath component of power Gi, at delay tau I. So power, this is the power multipath component of power, and this is the corresponding delay. So basically what this is saying is, this is the channel power profile, the wireless channel power profile. What this is saying is basically that there is a power of Gi which is arriving, that is, there is a component of power or gain Gi which is equal to magnitude Ai square, which is arriving at a delay of tau I. So this is a power Gi, this is a path power Gi which is arriving at a delay of tau I. Right? Is that clear? Is that clear to everyone? Right. So I can also represent a wireless channel by the power profile. Let me try to give a sample plot of how this power profile looks. For instance, let's say I have the time Then at tau 0, that is a delay corresponding to 0, I have a power of G0. At tau 1, I have power of G1, so on. At tau L minus 1, I have power of L minus 1. So that is basically my power profile. So what I'm saying is this is a power profile. This is a power profile of the wireless channel. At delay tau naught, I have gain G0. At delay tau 1, I have gain G1, so on and so forth. At delay tau L minus 1, I have gain GL minus 1. So G0 at tau naught, G1 at tau 1, so on and so forth, GL minus 1 at tau L minus 1. So G0. So basically what you are saying is that the power of the wireless channel, this is spread over this delay. The power of the wireless channel is basically spread over this delay, that is ranging from tau naught to tau 1, so on so forth, up to tau L minus 1. That is, I have a component with power G0 arriving at delay tau naught. I have a component with power G1 arriving at delay tau 1, so on and so forth. I have component with power GL minus 1 arriving at delay tau L minus 1. So unlike a conventional communication system with a single path of propagation, I have basically multipath. And these multipath components are arriving at different delay arriving different powers at different delays, right? So this power, basically unlike conventional communication channel in which I have a single path, unlike a communication channel in which I have a single path, in the multipath communication channel I have multiple components with different powers. These different components are arriving over different delays, and this delay, this period over which these different components are arriving, this is termed as the delay spread. This is termed as the what is the delay spread? What is the significance of delay spread? See, understand this concept of a delay spread. In a conventional communication channel, that is in a wireline communication system, there is no multipath propagation. So if you look at a conventional communication channel, its power profile is simply going to look like this. That is only one component, right? Because there is no multipath propagation. In a conventional communication system, because there is no multipath propagation, right? There is only one component, therefore there is only one component, and therefore there is only a single delay at which there is only a single instant of time at which all the power is arriving. However, in a wireless communication system, because you have multiple components because of the multipath propagation, these multiple components corresponding to the multiple scattered paths arrive at different instances of time. So one arrives at tau naught, one is arriving at tau 1, so on and so forth, one is arriving at tau L minus 1. So these different components with different powers, they are arriving at different time instances. So naturally what you have is you have a delay. There is a delay of time, there is a time interval over which these different components are arriving, and therefore there is a delay spread. What is the delay spread? The delay spread is the interval of time that is starting from tau naught to tau L minus 1 over which the power or over which the power of the wireless channel is concentrated, or over which the different multipath components are being received at the receiver. Right? So the multipath delay spread, the delay spread is basically an interval of time over which the multipath components are arriving at the receiver. So in a wireless channel, so let me define delay spread. Delay spread is basically the interval of time over which the multipath components are delay spread is basically the interval of time over which the multipath components are being received. So delay spread is naturally the interval of time over which the multipath components are received, and this delay spread is inherently, it's characteristic to a wireless environment because of the multipath propagation environment. Remember, if there is no multipath propagation, if there is only a single path, then can someone tell me what is the delay spread in this kind of scenario? When there is a single path, what is the delay spread in this kind of scenario? What is the delay spread for a single path scenario? Can someone tell me what is the delay spread for a single path scenario? Yeah, when you are single path, the delay spread is 0 because there is no interval of time, because there is only a single component that is arriving at one instant of time, right? So there is no spread, or there is no interval for which, and therefore the length of the interval is 0. So if you have a delay spread, if you have basically, we are not saying that the time of arrival is 0. What we are saying is basically that there is only one path component, and therefore the interval that is associated with this multipath component is 0 because all the energy is arriving at a single instant of time. I hope that part is clear. Alright, so multipath in wireless communication systems, because of the inherent nature of the multipath propagation, that is different components are arriving at different instants of time, there is a whole interval of time over which the different multipath components are arriving, and this is termed as the delay spread. This is termed as the delay spread. Okay, fine. Now let us go on to the next. What is the approximate delay spread? Let us consider an outdoor wireless channel scenario. Let us consider an outdoor wireless channel scenario. Now if we consider an outdoor wireless channel scenario, let us consider it a typical cellular scenario. Now, in a cellular system, if we look at a conventional cell, I am approximating it as a hexagonal cell. It need not be hexagonal, it can be some arbitrary shape, but this is simply to get an idea of what is the typical data. Let's say I have the base station. At the center of the cell, let's say I have this is the base station, and let's say I have the mobile at the edge of the cell. Now let's say I have a direct path. Now, can someone tell me what is the typical radius of a cell in an outdoor environment? What is the typical radius? What is the typical cell radius? Can someone tell me what is the typical cell radius in an outdoor environment? In a cellular communication system, what is the typical radius of the cell? Can someone tell me what is the typical radius of the cell? Outdoor communication. In an outdoor, what is the typical radius of the cell in a typical cellular environment? What is the typical? Yeah, getting the correct answer from SGGI SIT. It's typically of a few kilometers, right? About 5 kilometers, about 5 to 10 kilometers or something. Typically, it is approximately of the order of kilometers, right? Typically, it's of the order of kilometers. Conventionally, cellular radius are approximately of the order of kilometers. So let's say I have a signal direct path which is approximately of the order of kilometers, and then I have some path which is reflected again, which is approximately of the order of kilometers. Right, so all the distances are of the order of kilometers. Therefore, right, let's take an approximation. Let's say this direct path is of 1 kilometer, that is, and indirect path D2 is 2 kilometers. What I'm saying is that there are two paths. This is the direct path or line of sight path which has distance of 1 kilometer, and this D2 corresponds to non-line of sight path of distance 2 kilometers. Therefore, can someone tell me what is the approximate delay spread in this scenario? Can someone tell me what is the approximate delay spread in this scenario? What is the approximate delay spread in this scenario? Now, the delay spread is basically the difference in the propagation time, right? The delay spread is basically the difference in the propagation time, right? So propagation time corresponding to distance d1 is d1 divided by c, and propagation time corresponding to d2 is d2 divided by c. So we have a component which is coming at d1 divided, so there are two components. One is coming at d1 divided by c, other is coming at d2 divided by c, and there are only two components. Therefore, what is the delay spread? Can someone tell me what is the delay spread in this scenario? What is the delay spread? Therefore, can someone tell me in this scenario what is the delay spread in this scenario where I have two components? One is of d1, other is of d2, and what is c? C is basically, c is the, what is c? Can someone tell me, although I have not explicitly defined it, what is c? This is a fairly standard quantity. What is c? Can someone tell me what is c? Yeah, the delay spread is d2 minus d1 divided by c, that is 1 by c. So delay spread equals d2 by c minus d1 by c equals 1 by c. Okay. What is c? Yes, that is correct. C is the velocity of light. That is the velocity of propagation of the electromagnetic wave. So that is also natural because C is because the signal, the radio signal is an electromagnetic wave. Therefore, C is the propagation. This is the velocity of propagation of the EM wave, which is basically equal to 3 into 10 to the power of 8 meters per second. Therefore, what I have is basically d2 minus d1, that is 1 kilometer divided by c. So delay spread equals 1 kilometer, which is 1000 meters, divided by 3 into 10 to the power of 8 meters per second. Can someone tell me what is the value of delay spread? No, 3 milliseconds is not the correct answer. Can someone tell me what is the value of delay spread? Yeah, 3 microseconds. This is approximately 3 into 10 to the power of 6 minus 6 seconds equals 3 microseconds. That is 0.33 into 10 power minus 5. That is correct. That is 3.33 into 10 power minus 6. This is approximately 3 microseconds. What I am saying is the following thing, that I am saying in outdoor cellular environments, the distances are approximately of the order of kilometers. The distances are approximately of the order of kilometers, which means the delay spread or the interval of time over which the signals are arriving is approximately of the order of microseconds. So basically what we are saying is the following thing. In outdoor cellular environments, distances are approximately of the order of kilometers. Therefore, the delay spread, which is basically inversely proportional to distance or velocity, therefore the delay spread, which is basically not inversely proportional to distance, but distance divided by the velocity of light. So in that sense, directly proportional to the distances or the differences of distances, that is basically of the order of microseconds. Therefore, delay spread is of order of microseconds. The delay spread is typically of the order of microseconds. Right? This part is clear to everyone. Therefore, the delay spread, typical delay spread, is of the order of microseconds. Right? So, typical outdoor delay spread are of the order of microseconds. Now, what we want to do is we want to characterize delay spread. How do you characterize the delay spread given a power profile? How to characterize? So, our question, our immediate question is as follows. That is how to characterize a delay spread given a power profile. That is, given a channel power profile, how does one characterize the delay spread? That is, if we go back to this picture that we have over here, we have a power profile G0, G1 up to GL minus 1. That is, we have this power profile. Given such a power profile, how do you characterize the delay spread? So basically what we have over here is basically, let's say I have a power profile given such a power profile, that is basically power G0 at time tau naught, power G1 at tau 1, so on and so forth, GL minus 1 at tau L minus 1, that is given this power profile, how do you characterize the delay spread. Given this power profile, how do you characterize the delay spread of the given this power profile, how do you characterize the delay spread? Well, one way to characterize the delay spread is obvious. That is, I take the first arriving path, and that is what we have done, and I take the last arriving path, that is tau 0, tau L minus 1, and I simply say that the delay spread is delay spread equals tau L minus 1 minus tau naught. That is the delay of last arriving path minus delay of that is simply the delay spread equals the delay of the last arriving path minus the delay of the first arriving path. That is, the delay spread is simply the delay of the last arriving path minus the delay of the first arriving path. So delay spread is basically tau L minus 1 minus tau naught. Tau L minus 1 is the last arriving path, right, and tau 0 is the first arriving path. So delay spread is basically this. We are saying that this is the interval of time over which the multipath components are arriving. So simply this can be put as the delay of the last arriving path minus the delay of the first arriving path, that is tau L minus 1 minus tau 0, and this is known as the maximum delay spread. That is basically this is tau L minus 1 minus tau naught. This is known as the maximum delay spread. This can be denoted by the notation sigma max. So I will call this as the notation. This can be denoted by sigma max is basically the maximum delay spread. What is the maximum delay spread? The maximum delay spread is basically the spread. That is basically, it is a measure of the delay spread. What is the maximum delay spread? It's basically an indicator or a measure of the delay spread. It can be obtained as follows. Simply take the last arriving component, that is the delay corresponding to the last arriving component, and take the delay corresponding to the first arriving component. Therefore, the maximum delay spread equals tau L minus 1 minus tau naught, which is basically the spread of the delay in which the different multipath components are arriving. Alright, this is tau L minus 1 minus tau naught. That is the spread over which the different multipath components are arriving. This is the maximum delay spread. Alright, this is the maximum delay spread. This is spread of components over which, spread of time over which the different multipath components are arriving. So this is the maximum, this is the maximum delay spread. Okay, this is the maximum, this is spread of time over which different multipath components are arriving. So this is the maximum delay spread. Alright, now for instance, let us take an example again. Let's say I give you an example. Now again, you have to observe that for maximum delay spread, I don't need to know the intermediate values of the delay spread. That is, I don't need to know tau 1, tau 2, etc. I only need to know tau 0 and tau L minus 1. Also, I don't need to know the different gains, that is G0, G1, GL minus. Obviously, this is a poor measure, but at least it's a basic measure which can serve some purpose. For instance, let us take an example. Let us take an example where tau 0 equals 1 microsecond and tau and let us say L is equal to 4, that is, I have 4 multipath components, and tau 3 equals 5 microseconds. Can someone tell me what is the maximum delay spread? So the example I am giving is as follows. we have tau 0, I have L equals 4, tau 0 equals 1 microsecond, tau 3 equals 5 microseconds. What is the delay spread? What is the maximum delay spread? Maximum delay spread is clearly tau 3 minus tau 0 equals 5 minus 1 equals 4 microsecond, right? So the maximum delay spread is basically 5 minus 4, 5 minus 1, that is 4 microseconds. That simply says that this is the interval of time over which the signal is arriving at the receiver. Alright, that is the interval of time over which the signal is arriving at the receiver. Now this is, of course, this is a slightly bad measure of the delay spread. The reason being the follows: because you can clearly see we are not giving any importance to either the gains, that is G0, G1, GL minus 1, or some of the components, that is tau 0, tau 1, tau L minus 1. For instance, can someone tell me when there can be problems with this delay spread? Can someone tell me when this is not an appropriate measure of the delay spread? So this is the maximum delay spread, that is sigma max. When can there be problems with this kind of a measure of delay spread? When can there be problems with this kind of a measure of delay spread? Correct? Someone is saying when power variation is not uniform. Can you elaborate on this? What do you mean when the power variation is not uniform? Correct? What you are saying is correct. Can you elaborate on this a little bit more? What do you mean to say when the power variation is not uniform? Yeah, one of the problems with this could be the following thing. When two components are at the same, well, that is not exactly what I had in mind. There is no problem in that case, but let us consider the following scenario. Power decreases with, correct, as the power decreases with distance. Yeah, that's, I think I'm getting an idea of what you're trying to say. So let me just give an example. For instance, let us say I have a multipath delay profile which looks as follows. For instance, let's say I have a large number of paths, but the multipath power profile is decaying. Then after some time I have a large paths with very small power. Now if I simply say that the delay spread is corresponding to this, it might not be a significant measure, right? Because several paths that are corresponding to this have very low power. For instance, here several paths which are corresponding to this have very low power. So the power in the paths that arrive later might not be significant corresponding to power in the paths that are arriving earlier. So these low power paths, these are not significant, right? These are insignificant, not significant in terms of, they might not have significant power. Therefore, a correct measure of the delay spread will have to weigh the delay. That is what I have to look at, is I have to look at the weighted delay. I have to look at the weighted delay. That is, I have to weigh each delay corresponding to the power in the delay. That is tau 0, each delay tau I has to be weighted in what I am saying is the following thing, that each delay tau I has to be weighted. That is, we have to weigh it. That is, we have to weigh it by the proportion of power corresponding to that path. Is that clear to everyone? That is, each delay tau I, this has to be weighted or weighed with corresponding to the proportion of the power. For instance, what is the power that is in path tau I? Power in path tau I is Gi. Now what I'm going to do is I'm going to create a fraction Bi such that Bi equals Gi divided by G0 plus G1 plus GL minus 1. That is, basically this is power in, that is, if I were to define it, that is, what is Bi? Bi is basically the power in the ith path, that is Gi, divided by the total power, that is G0 plus G1 plus so on up to GL minus 1. Therefore, this power in the ith path divided by total power, this is nothing but this is the fraction of power in ith path. Can everyone see that? This is the fraction of power. This is the fraction of power in the ith path. Bi is the fraction of power. Bi is a fraction of power in the ith path. Now can someone tell me what is the summation of all Bi? That is, what is B0 plus B1 plus BL minus 1 equals, can someone tell me what is B0 plus BL? Summation of all B0 is 1, right? Everyone can see therefore that each B0 is positive, that each Bi is positive, and summation of all Bi is 1 because Bi is a fraction, that is a fraction of power in the ith path. Total of all fractions is basically nothing but total power divided by total power, which is basically 1. Okay. Now I want to define what is known as the mean delay. Now what I will do is I will weigh each delay by this fraction of power to define the mean delay. Mean delay tau bar equals B0 tau 0 plus B1 tau 1 . Look at what I am doing. Unlike what I did previously, what I am doing now is I am weighing each delay by the fraction of so now I am simply not considering T tau 0, tau 1, tau L minus 1, but I am weighing each delay, that is basically each delay tau 0, I am weighing it by the fraction B0. So the mean delay tau bar is basically B0 tau 0 plus B1 tau 1 plus so on BL minus 1 tau L minus 1, right? So basically there is some question saying what is BI called. I already defined BI is the fraction of power in the ith path, and this term is used for calculating the mean delay, that is tau bar equals B naught tau naught plus B1 tau 1 plus so on up to BL minus 1 tau L minus 1. Now this is the mean delay. Also we can calculate it in terms of the G naught. Therefore you can see this is G naught divided by summation Gi into tau naught plus G1 tau 1 divided by summation of Gi plus EL minus 1 tau L minus 1 divided by summation of Gi, which is equal to summation of Gi tau I divided by summation of, yeah, can anyone see this? This is equal to the summation of Gi tau I divided by summation of Gi. Therefore the mean delay, I can say mean delay equals summation Bi tau I equals 0 to L minus 1 equals summation I equals 0 to L minus 1 Gi tau I divided by summation I equals 0 to L minus 1 Gi. Right? So basically the mean delay tau bar equals either summation Bi tau I, which is equal to summation Gi tau I divided by Gi. Okay. So in this basically we have started our new chapter, that is characterization of the wireless channel. That is basically what is our aim in this chapter. The aim in this chapter is to basically study the various parameters that characterize the wireless channel. Delay spread is one such parameter. The delay spread is the delay over which the signal is arriving at the receiver. This is termed as the delay spread of a wireless channel. And what we have done is we have started characterizing the delay spread of the wireless channel. So I'm going to stop here and I will continue in the next lecture. I hope what I've said is clear. I will continue again in the next lecture. Alright? Thank you. Thank you very much.